Right now, over at CERN, physicists are basically in the middle of this epic, cosmic detective story. They're running one of the most fundamental experiments you can even imagine, all to answer a question that honestly sounds almost ridiculously simple.
Yeah, that's it. That's the big question. Does antimatter, the mirror image of all the stuff that makes up you, me, the planet, everything, does it react to gravity the same way, or does it do the exact opposite? Does it fall up? And look, getting this right is a huge deal. Our best theories say the Big Bang should have cooked up equal amounts of matter and its sort of evil twin, antimatter. But, just look around. We live in a universe that's all matter. Figuring out how antimatter handles gravity is a massive clue in the mystery of where it all went. The problem, though, as you can probably guess, is you can't just make an anti-apple and let it go.
You see, the second antimatter even grazes normal matter, poof, they both vanish in a burst of pure energy. So you can't hold it, you can't put it in a jar, you can't even let it touch the air. This makes trying to study it, well, incredibly difficult.
It's actually pretty simple when you break it down. All the charges are just flipped. So a normal hydrogen atom has a positive proton and a negative electron, right? Well, antihydrogen is just the reverse, a negative antiproton and a positive positron, and is this super simple anti-atom that the scientists at CERN set out to build.
So how in the world did they pull it off? To even attempt this, they had to build a place that is totally one of a kind, the Alpha Experiment, located at CERN's antimatter factory. The whole point of this place is to create, to hold on to, and to study these incredibly shy anti-atoms, using what's basically a super high-tech cooking recipe.
So think of it like a recipe, but, for creating bits of an anti-universe. It's got three main steps. First, you've got to get your antiprotons. Second, you gather up your positrons. And third, the really tricky part, you have to mix them together very, very carefully inside a special magnetic trap. Okay, ingredient number one comes from CERN's own anti-proton decelerator. The Alpha Experiment has this thing called a catching trap, and it snags about 100,000 antiprotons from every single pulse. But they're way too energetic, so they use electrons to cool them down, kind of like a brake, to get them nice and calm for mixing.
For ingredient number two, they have a whole other machine that collects millions of positrons. These actually come from a simple radioactive sodium source. And just like the antiprotons, they get cooled down, this time with nitrogen gas, getting them ready for the final step.
And this is where things get really delicate. The two cooled clouds of antiparticles are ever so gently merged together in the main mixing trap. You have to do it just right. If you mix them too fast or too violently, the anti-atoms you make are too hot. They're moving around too much, and there's no way you'll be able to trap them for the experiment. Now, for years, this whole process was honestly super slow and inefficient. They could only make a few anti-atoms at a time. But then, they had this revolutionary breakthrough in cooling that just completely changed the game and let them make antimatter like never before.
And the solution they came up with was just so clever. They basically threw a third type of particle into the mix, laser-cooled beryllium ions. Think of these ions as microscopic ice cubes. By letting them gently bump into the positrons, they cooled the whole positron cloud down to incredibly low temperatures. It created the absolute perfect conditions for forming lots of nice cold antihydrogen.
The results were just mind-blowing. The spokesperson for the experiment, Jeffrey Hangst, he put it perfectly. He said, "These numbers would have been considered science fiction 10 years ago."
So what does that actually mean? Well, get this. This new technique boosted their production rate by 8 times. 8! They could suddenly make over 15,000 antihydrogen atoms in a few hours. Before this, that would have taken them weeks to accomplish. A total game changer.
Okay, so they've got this steady supply of super cold antihydrogen. Fantastic. But now comes the real moment of truth. How do you actually hold on to these things, which have no electric charge, long enough to see which way gravity is going to pull them? They use something that sounds straight out of sci-fi, a magnetic bottle. See, even though the antihydrogen is neutral, it acts like a tiny, tiny compass needle. It has a magnetic moment. So the experiment uses this really complex set of powerful magnets to create a little sweet spot in the middle, where the magnetic field is at its absolute weakest. The antiatoms just naturally get drawn there and float, suspended in a perfect vacuum, not touching a single thing.
So how do you actually run the experiment? Well, the method is kind of beautifully simple and also totally destructive. You just
Turn the magnets off. The bottle disappears. The anti-atoms are now free and gravity takes over. All you have to do is watch and see if they hit the detector at the top of the chamber or at the bottom.
What the scientists are hunting for is something called the annihilation vertex. It sounds complicated, but it's just the exact 3D coordinate, the precise point in space and time where that anti-atom finally hits the wall and goes poof. That little flash of light tells you everything you need to know.
To find that exact spot, they need this incredible piece of tech, basically a super high-tech 3D camera. When an anti-atom annihilates, it sprays out other particles. The detector tracks the exact curved paths of these fragments. And then, kind of like a high-tech forensic analyst, it traces all those paths backward to the one single point they all came from. And that's it. That's the vertex.
All right, so after all those years of building, of perfecting the recipe, of painstakingly collecting thousands and thousands of these little flashes of light, they finally had enough data. They could finally answer that huge, fundamental question we started with.
So, does antimatter fall up? The answer, after all that work, is no. Antimatter falls down. The data was overwhelming. The vast majority of those little annihilation flashes happened at the bottom of the chamber, not the top. It behaves just like regular matter under gravity.
Okay, so what? It falls down. Why is this such a massive deal? Well, first, it's a huge confirmation of Einstein's theory of general relativity. Second, it slams the door on this really cool but exotic idea that anti-gravity is why we don't see any antimatter lying around. And by doing that, it actually makes the original mystery even more profound.
Which leaves us with this giant, nagging question. If the Big Bang made matter and antimatter in equal amounts, and now we know for sure that gravity treats them exactly the same, then there must be some other secret difference between them that explains why one built the entire cosmos while the other just vanished. And figuring out what that is, well, that's now one of the biggest unsolved mysteries in all of science.